So, good morning to all. Good morning, Professor Devdeep Jaina, our today's orator, our chief guest, Shri Nilesh Desai, Dr. Seema Vinayak, our director. And there is no ex-director, they have not joined us, no problem. And professors, scientists, researchers, and staff here and online. Sir J.C. Bose, a name. He was a multifarious personality, a radio pioneer, botanist, physicist, scientist, who patented first semiconductor rectifier of the world in 1901, named as cat's whisker. It was a metal semiconductor diode. And the whole revolution of today's semiconductor technology based on those developments that happened in that era. It was too early for him, but today we still remember because we are working in that field, semiconductor devices. Today we are organizing our 7th Sir J C Bose Memorial Oration in commemoration of 60th Raising Day of SSPL. This lecture series was started in 2016 on 54th SSPL Raising Day. Last year we organized this lecture online due to the ongoing COVID pandemic. This year too, we are organizing this lecture through WebEx and broadcasting on YouTube. Now I invite Dr. Seema Vinayak, OS and Scientist H and Director SSPL to welcome all participants. Yes, ma'am.
Shri Nilesh Desai, Distinguished Scientist and Director SAC, Professor Devdeep Jaina, all my seniors who have joined online, and especially I would like to mention Dr. M. Gopal Rao, who has joined. I happened to talk to him yesterday. He is probably the first few people who joined SSPL, and he has contributed a lot to the history of SSPL that has got compiled now. So my special welcome to him. And welcome to all the all the audience who are present here from SSPL. Today, as Janesh just mentioned about it being the 7th J C Bose Memorial Lecture, and it is special for us. Why? Because it is the 60th Raising Day that we are celebrating, and this just happens to be one day before that and part of the celebrations of our 60th Raising Day. It's a special occasion for SSPL, and I'm really, really thankful to Professor Devdeep Jaina for accepting our invitation, because it is quite an unearthly hour in the US, and he's there in the office for talking to all of us. I would just say that, as Janesh mentioned, Sir J C Bose is a very, very inspiring physicist for all of us. I would say he was a physicist who applied his physics to plants and biology, and the one who pioneered the work in radio science, and also was acclaimed as a scientist 60 years ahead of the times then, because he was the first to mention that P and N type semiconductors will have to be put to use. So for SSPL, it's a very, very relevant area that Sir J C Bose worked in, and therefore he will continue to be a very, very inspiring figure for all of us. And on this occasion, it is our pleasure that we have Mr. Nilesh Desai as the chief guest, who right now is at the most advanced stage of the wireless communication that Sir J C Bose started. He is now into satellite communications. And we have Professor Devdeep Jaina, who's talking about the high-speed RF devices and the quantum devices on GAN. I just take this opportunity to introduce our chief guest, and then I would request him to introduce our speaker. So Shri Nilesh Desai, a distinguished scientist, is currently the director of Space Application Center, ISRO, Ahmedabad. He's BE Electronics from Gujarat University, Ahmedabad, and has more than 35 years of dedicated and illustrious engineering and research career at SAC. He has been instrumental in the design and development of ISRO's microwave radars. He has contributed immensely to the advanced applications involving Earth observations, navigation, and communication technologies for societal and strategic uses. Presently, he is guiding activities related to remote sensing data processing, NAVIC receivers and applications. NAVIC is navigation with Indian constellation, and his leadership in the activities involving SATCOM terminals, ground communication through mobile, broadband, and high throughput communication satellites has provided direction and strengthens space infrastructure and its applications. He has represented ISRO at various international forums, and he's the recipient of ISRO Performance Excellence Award, ISRO Individual Merit Award, and ISRO Team Award for RESAT-1 payload for the year 2012. He's holding the positions of National President of Indian Society of Remote Sensing and Indian Society of Systems for Science and Engineering. May I now invite our chief guest, please say a few opening remarks and also introduce the orator of the day to the audience. Thank you.
Thank you, Dr. Seema. And good morning to all the participants. And let me welcome and greet Dr. Devdeep Jina ji for agreeing to give this talk. And we eagerly look forward to his talk. Now, before I come to that, let me also greet the SSPL community and all associated with SSPL on the eve of their 60th Raising Day, which falls tomorrow. And we are fortunate to have Dr. Devdeep Jina for the 7th J C Memorial Oration here today, which will benefit all our participants as well as all those who are seeing it on YouTube as well. So let me greet all of you and welcome you for this very important lecture and oration by Dr. Devdeep Jina. And as Dr. Seema and Mr. Janesh Kaushik has already pointed out, the JC Bose having done this pioneering work in this field related to technology as well as science. And now since we are embarking on new development, especially related to quantum frontiers, so this is an apt occasion to listen to expert like Dr. Devdeep Jina. So let me welcome sir once again and for agreeing for this talk. And we eagerly look forward to your talk on high-speed RF electronics and quantum devices with nitride semiconductor. Now we at Space Applications Center, a center of Indian Space Research Organization. It is one of the multidisciplinary and a unique center among ISRO because ISRO's other centers do specific targeted activities, whether related to rocket launches or related to satellite development. But unlike that, our center here in Ahmedabad adopts a multidisciplinary approach. Means we do hardcore technology development also in sensors and various electronics associated with that for payloads, which we build for communication, navigation, and various remote sensing radars as well as camera systems. And apart from that, we do applications also. So in that sense, it is a very holistic approach which we follow here at Space Applications Center. And recently we have embarked on, of course, AI, ML, and all these are buzzwords. But quantum frontier is one another mission which is identified under our Honorable Prime Minister's Scientific and Technical Advisory Committee. So there, this quantum frontier is the area in which last couple of years we have started working on that. And that's why this lecture has come at the very appropriate time, I'll say. And now having gone through Dr. Devdeep Jina's CV, I would just like to now brief all of you and introduce our distinguished speaker of today, Dr. Devdeep Jina. Dr. Jina is the David E. Berg Professor of Engineering at Cornell University, one of the most renowned Ivy League university. All of you are well aware of that. And incidentally, he was born on 26 November 1976. Now, 2611 is well known here in India. Of course, all of us don't forget 9/11 and 26/11. So Sir is in the Department of Electrical and Computer Engineering and Material Science and Engineering at Cornell, and is a field member in the Department of Applied and Engineering Physics. So it is a unique mix of various activities which we do related to electrical and computer engineering as well as material science and engineering. So this is a unique combination. And as I said, we eagerly look forward to hear from you about the activities related to material science, which applies into the various fields of electronics as well as computer engineering. Dr. Jaina joined Cornell in 2015. And of course, I forgot to mention, he is an alumni from IIT Kanpur, having done his major in electrical engineering and physics as a minor in 1998. And then he joined Cornell in 2015 from the faculty at Notre Dame University, where he was earlier from, I think, 2003 onwards. He taught at Notre Dame University, and shortly after earning his PhD in electrical and computer engineering from University of California, Santa Barbara, UCSB, then he joined Cornell in 2015. His teaching and research are in quantum physics of semiconductors and electronics and photonic devices based on quantized semiconductor structures, that is nitrides, oxides, and 2D materials. So incidentally, these are the fields on which we are now starting working here in ISRO also, as well as SSPL has been very well known for various activities related to gas and GaN devices. So considering that your oration has come at a very appropriate time. Now, sir's teaching and research are in the quantum physics of semiconductors and electronic photonic devices that I already mentioned. And apart from that, there has structures with superconductors, ferroelectricals, and magnets, with device applications in energy efficient transistors, light emitting diodes, and RF and power electronics, and quantum computation and communication. And incidentally, we are involved in right now quantum key distribution activity related to satellite-based quantum communication. And of course, we are also embarking on quantum computing related activities as well. So your experience and expertise in this field will surely help us a better insight into the other aspects related to that, especially related to molecular epitaxy related, MB related growth, as well as device applications involving 3 to 5 nitride semiconductors. The research from Dr. Jaina's group has been published in more than 300 journals, including in Science, Nature, Physical Review Letters, Applied Physics Letters, and Electronic Device Letters. Several patents have been granted for the group's research work. Dr. Jaina is also a fellow of American Physical Society and is the winner of teaching awards and research awards such as ISA's Young Scientist Award in 2012, MB Young Scientist Award in 2014, and awards from industry such as IBM Faculty Award in 2012, and most recently the Intel Outstanding Research Award in 2020. So, as I said, we are fortunate that will be able to learn more about this very exciting field, and especially I was going through your other areas of research that is related to how you marry the semiconductor as well as superconductor technologies. So we would like to hear something on that as well. So, sir, let me welcome once again before this august audience here, and we all of us are very eager to listen to Dr. Devdeep Jaina on this field of expertise. Welcome, sir. And I request
thank
you
so
to
much.
start your presentation.
Can you hear me?
Yes.
Thank you so much, Mr. Desai. I'm very flattered, honestly, with your very kind introduction. And also thank you to Dr. Seema as well as Ganesh for the invitation. And I honestly, being from India, I feel very proud every time I hear and see about ISRO. So I think we all make every Indian around the world proud. And I can only consider myself fortunate if I can be of any help in any way. Please just ask. I would. It would be my honor. So likewise with SSPL, I've known colleagues from SSPL for a while, so I'm also very honored to that you invited me and gave me this opportunity to present. So I'll share my screen now, and hopefully it shows up okay, and then we can get started. Sorry. Yep. Does it look fine?
Yeah, it's very
Yeah.
good.
Yeah. Okay. So as Mr. Desai just introduced, I will speak about some of the recent work that we are doing in research of high-speed RF electronics and quantum devices with which involve nitride semiconductors as well as nitride. Towards the end, we will talk a little bit about nitride superconductors and their integration with nitride semiconductors. This work is done in very close collaboration with my colleagues here at Cornell, Professor Grace Shing and Professor David Mueller. And also the middle part of the presentation, as well as some of the early part, is in collaboration with Intel. And as probably many of you are very well aware, Intel has seriously started investigating in the next big semiconductor after silicon, and that is, of course, gallium nitride. And we will see a little bit of what they are doing and what we are also kind of working with them to do. And the work is supported by various agencies, including DARPA and Semiconductor Research Corporation and the National Science Foundation as well. So I'm really honored, honestly, to be a speaker in the Jagdish Bose Memorial Oration this year. I just finished writing my first sort of textbook, which is on quantum physics of semiconductor materials and devices, that is about to come out later this year. And this is just something in the book which I have felt very fortunate to include, well before people like Marconi, J C Bose had already realized that a Schottky diode rectifier can be used and demonstrated that it can be used for basically a millimeter wave detection and radio receivers. As far as I know, he was the real inventor of the radio, but he really disliked patents. He disliked commercializing things, so he didn't go ahead and do that. Whereas Marconi was definitely a salesperson, so he went ahead and did that. Among his many contributions, as was mentioned by Dr. Seema and as well as Ganesh and Nilesh here, that he put his knowledge in physics to many areas. I grew up in Asansol in West Bengal when I was a child, and I know in Calcutta there's a Bose Institute, which is not for radio or microwave, but it is for biology and botany and other things, which is just very impressive as the intellectual breadth of a person. My intellectual breadth is 100th or less than that of J C Bose, so I will only talk about electronics and materials and physics today. But I just want to start by saying that I feel extremely fortunate since my graduate school because in research, because I got started working around the turn of the century, 1999, 2000, when I started grad school to work on gallium nitride. And I had no idea at that time, and neither did my advisor or other people, how big it is going to become. In fact, it is undoubtedly the biggest revolutionary semiconductor since silicon. A lot of it really comes from photonics, from lighting, which created the big industry. But now electronics has a chance to be as big or even bigger than what photonics has done for solid state lighting. So we must dream big with nitride semiconductors. We should not think of it as another semiconductor which will never be as big as silicon, because it is already very big. It's in all our cell phones as LEDs, in all our laptops as backlighting, and it is increasingly in most base stations. So we must dream big. So what do I mean? Whatever we are dreaming about here, I'm going to share a little bit with you. Of course, the first points of introduction of gallium nitride in the RF and millimeter wave domain, especially in the RF domain, are in base stations. And I do know that, for example, even here in a small town, Ithaca, in upstate New York in US, the base stations are being slowly replaced by gallium gas devices are slowly being replaced by GaN. I know that in Japan, for example, also Mitsubishi and many of the companies are taking up that job. Of course, this has a lot of importance because it's a commercial space, but as we know, commercial space comes with the fact that much higher frequencies are also possible with this material. Now, if we look at a system today, RF system today, there's a transmit and a receive side of it. And the high frequency power amplification, of course, is desired for wireless communications. And if we look at the power amplifier, of course, the basic job is to take a small signal and amplify using a transistor to a large signal. And more power at high frequency is always the desired goal. So I will, through the presentation, use a few slides of students who graduated recently, and this one is from Reed Chaudhary, and you can see it is from his PhD defense, and they kindly agreed to share it with me. So we have the trade-off for any given material technology based on semiconductor material platform. Which semiconductor did we choose? If it's gallium arsenide, it has a certain critical electric field. It has certain saturation velocity of electrons, and that limits the amount of speed and breakdown voltage product one can get. And it, of course, going to higher speeds, we get less power because we have to make the device small. And when we make it small, it breaks down, so we can apply less voltage, and less voltage times current is less power. So, so this is the trade-off. And of course, we know that compared to gallium arsenide, gallium nitride extends the amount of voltage you can apply, and therefore the power handling capability is much larger. And that's why in this picture, the space in RF arena that gallium nitride is starting to move into is in the really high frequency and high power domain. Now, that being said, one can wonder what about even higher powers and higher frequencies? There is never an end to how much power and how much high frequency do we need for needs for all kinds of communications, ranging from SATCOM to defense to astrophysics and radio astronomy, as well as terrestrial communication systems and communication links. So it is very natural to think that why stop at gallium nitride? Why don't we go to even larger? Of course, we're going to use gallium nitride all the time, but we are going to use it for its very high mobility of carriers. But in the areas that GaN doesn't perform well, it performs very well, but there are many semiconductors which can do better. And one of them is aluminum nitride, which is basically the same platform. Whoever grows gallium nitride can also grow aluminum nitride. In fact, gallium nitride transistors have aluminum gallium nitride channels, as barrier, and therefore the aluminum source is already there in the epitaxial system. If we look carefully at aluminum nitride, it has a higher thermal conductivity than gallium nitride. It has a higher breakdown field than gallium nitride, but it has a lower electron mobility than gallium nitride. So what we have started doing, and I will share a little bit with you as a next generation technology beyond gallium nitride, is something I'm going to share with you. So just a second, if you don't mind, I think I skipped this. Here's an example of gallium nitride based transistors, which is sort of the state of the art, which is integrated very, very closely with silicon. Many of you probably have seen this. This was reported 3 months ago by Intel, and this is their internal project where they have integrated on 300 millimeter silicon. They have integrated gallium nitride with silicon PMOS acting with gallium nitride NMOS channel. In fact, they are seeing that gallium nitride N channel transistor, even for digital, is going to outperform silicon, and that is incredible. And they are integrating it at a very high density now. They can make digital inverters with gain. But of course, the more important reason why they're integrating with silicon is because you can have silicon CMOS in very close integration with GaN RF. They are able to push FTF maxes of these gallium nitride HEMTs that are integrated directly with silicon to close to 300 gigahertz FT and 400 gigahertz Fmax. It's an E-mode device, here's a result from our university, our group at Cornell, led by Grace and me. You can see that we reach 200 gigahertz Fmax, but 250 on silicon. But of course, Intel, being Intel, they enter the chart at the top. Not only for RF, they show decent power amplification. They also show power distribution on chip. And here lower is better. So they are able to show that they are able to beat silicon LDMOS by a factor of 10. Just because GaN has a wider band gap and larger breakdown. So that's just incredible in my opinion. And not just GaN HEMTs, but FinFETs. These are very, very narrow fins here with side gates and conduction this way, and they're able to kind of do that. So this is not just us. I mean, big companies like Intel are also dreaming big about gallium nitride, and I think that's a very, very good thing for the ecosystem. Let me see what we are trying to do. I talked about the power amplifier is one component. And here aluminum nitride has this advantage of larger thermal conductivity because a lot of the RF amplifiers today are choked by heat and not so much by breakdown anymore, but by heat. The other end of the spectrum is a filter. And we all know that the RF filters at low frequencies, not at high frequency, but at low frequencies, about 10 gigahertz or lower, are all based on aluminum nitride. These are sputtered, and these are typically bulk acoustic wave filters or BAW filters. It used to be surface acoustic wave, but now it's all FBAR or bulk acoustic wave. And in order to have, say, 15 channels, you have 15 BAWs, all integrated of different thicknesses to tune into that, CDMA frequency or that frequency or this frequency. This is, for example, the iPhone 12, a front end, there's power amplifier, the switch, the filters, and these are all right now different materials. Power amplifier is made of some material, the switch is made of some other material, filters are made of some other materials, such as silicon CMOS or GaN or GaAs or indium phosphide. We are really dreaming that why not make all of these with nitrides? In fact, it is very, very feasible, and not only feasible, it is going to become actually very attractive to make the filter, the LNA, the PA, the FBARs, the HEMTs, and of course the CMOS front end will be difficult with the LN, but I'll show you that it's not impossible. And already it's on silicon, so already you have that advantage. So what I'll show you now is how are we making N-channel transistors with GaN first. Then I'll talk about how are we making P-channel transistors with gallium nitride, not with silicon, but with gallium nitride and aluminum nitride. And then I will talk about the integration for quantum with superconductors, etc. So that's sort of the talk. Here's kind of a pictorial dream, so to speak. And here are some devices that we actually have demonstrated. So what we are doing at Cornell is we start with aluminum nitride buffers and on silicon carbide. So we have things like substrate integrated waveguides for about 140 gigahertz filters for really high speed networks. We have bulk acoustic wave because we are using aluminum nitride as the buffer layer. We can use this as an acoustic resonator, and this is a BAW filter. BAW filters currently we can reach about 10 gigahertz with just this, but as we scale it down, it will become more challenging, but we think we can push it maybe about to 20, 30 gigahertz or maybe 40 gigahertz, but not a whole lot more because then the efficiency really droops after that with the acoustic wave filters. And these are the people who are working on these individual aspects of nitride RF components. We have, of course, N-channel transistors, which is I will talk about as the first part of it. These are very, very ultra-scaled gate length transistors, which are starting to deliver power, RF amplification power at close to 100 gigahertz now. At 30 and other lower frequencies, they're good, but especially when you go to 100 gigahertz, it becomes very hard to get enough power, and these transistors are starting to kind of show very high promise in the initial results. And these are the people who are working on this. And then finally, I'll also show, in the middle of the talk, I will also show that we don't have to be limited to N-channel transistors with gallium nitride. In fact, we can make very decent P-channel transistors, which we will show that they are able to get up to about 40 gigahertz Fmax already today in the lab. I mean, not in production, but in the lab. And we are talking about 40 gigahertz P-channel transistor here, so that is this is an experimental data made by Kazuki and Austin and Sam and also Reith, of course, is the main person behind this. So this is kind of a big picture of non-quantum, but more on RF microwave integrated system based on aluminum nitride as the platform, but using these thin quantum wells of gallium nitride for channels for electrons and holes. So let me start with gallium nitride N-channel transistors for very high-speed RF and millimeter wave electronics. This work is done by Austin and Reith primarily. Both of them have graduated. I'll show what they're up to later. And Sam Bader and Reith are at Intel, and Kazuki Nomoto is the postdoc scholar here. So let me go over to that. This part, I think many of us already know, and there's excellent work, in SSPL on this, and I think probably ISRO may be considering use of this, or if not already using this already in some of their activities. But typically, gallium nitride HEMTs today, which are commercial, are based on gallium nitride with the aluminum gallium nitride barrier layer. Here's the energy band diagram, conduction band, valence band, a two-dimensional electron gas is formed because of polarization-induced electric fields at this interface, and this 2D electron gas has a pretty high mobility. That's our channel. For source and drain, we put a gate on top, and we can modulate the channel with the gate field effect from the gate, and we can get both switching or RF power. We can apply high voltages on the drain and make power switches, which is a huge area of application in power electronics. Or we can, bring the drain closer, make the gate smaller, and boost the speed, and use it for RF and millimeter wave. It's the same material, just slightly different geometry for different purposes. Now, with conventional aluminum gallium nitride GaN heterojunctions, we have already started hitting the wall in terms of how much power can we coax out of it. Can we squeeze out of this material layer? Because if the top barrier layer is aluminum gallium nitride, so we need a thick barrier to generate a very high density 2D electron gas that has a low sheet resistance. Therefore, you can get high speed, low parasitics. But if you have a very thick layer of barrier, you know that if you put the gate down, the gain will be low because the GM or transconductance is dependent on the thickness. The closer is the gate, the higher is the gain. So if the gain is low to start with at DC, of course, the frequency cutoff will be lower, so the speed will be low. There's no back barrier in this channel typically, and the 2D electron gas is confined very well from the top, but the quantum barrier in the back is very weak, so the electron sort of goes down. So when you scale the gate, it doesn't work that well. So ideally, a back barrier would be desired. Finally, the thermal conductivity of gallium nitride is actually very good, 220 watts per meter Kelvin. Unfortunately, it is not good enough because the gallium nitride transistor can generate a whole lot more power than what the buffer can dissipate. So it would be really nice to improve the thermal conductivity of the substrate by whatever means possible, even by 20 or 50 watts per meter Kelvin improvement is a great deal. It will help push or rather pull out a bit more power, squeeze out a bit more power from these devices. So here's what we are starting to slowly move towards, and I will kind of explain them slowly because when we were actually in a DARPA program back in 2010 to 2015, it was called the DARPA Next program, and there the goal was, can we make gallium nitride transistors that push up to 400 to 500 gigahertz speed limit, so that we can get a huge amount of power at 100 gigahertz from them. Because if the cutoff is, so we step back 1/3 or at least that much from the cutoff frequencies. And we realized at that time that if we use a GaN back barrier, it's going to be GaN buffer layer is very difficult. We got to move over to aluminum nitride. So we have replaced the substrate with aluminum nitride. There's no more gallium nitride in the substrate. It's all ALN. And what we are using is a very thin channel of gallium nitride. This picture doesn't do it justice because the GaN channel is about 30 nanometers only. Then the barrier on top of it is aluminum nitride. And then we have a top passivation layer of gallium nitride. In this structure, there is almost no gallium nitride, very, very thin layers. Almost the entire geometry is aluminum nitride. And therefore, and its band gap is 6.2 electron volts. Its thermal conductivity is 340 watts per meter Kelvin intrinsically compared to 220 of gallium nitride. So thermal conductivity is much higher. It has an enormous back barrier. It gives you the largest band offset, the largest back barrier that is possible in this material platform. And it gives you the largest top barrier as well, so that you can scale as much, the most you can desire from the top as well. So essentially, the structure combines the best of two worlds for heat and for top barrier and quantum confinement. We use the best material, that is aluminum nitride. But for the channel, which gives you the high mobility, we are using gallium nitride. So this is the rationale behind the change from this conventional heterostructure to this new heterostructure. When I say new, it is not a heterostructure that it requires a new epitaxy system, MOCVD system, or MB system. You can draw this in the same system that you have. It's just a different layer structure. So we started this, as I was mentioning, back in 2010, and here are some of the first results, because it's not trivial to grow gallium nitride on aluminum nitride and keep it strained. This is an important point. Gallium nitride here is not relaxed. It is strained, compressively strained to the aluminum nitride, because aluminum nitride has a smaller lattice constant. And then, therefore, the aluminum nitride on top is actually not strained. The barrier is not strained. Now, it is very difficult to make an ohmic contact through the aluminum nitride. So we actually etch it down and we regrow N++ gallium nitride on the sides, and we connect to the 2D electron gas from the sides. Very much like CMOS technology, so to speak. I mean, they are also using source drain regrowths in CMOS. And Intel also uses regrown contacts for the ones that I kind of just mentioned at the beginning. So here it's showing that the gallium nitride is indeed strained to aluminum nitride. This is a lattice constant. If it's in a vertical line, then they have the same lattice constant, aluminum nitride and GaN. And these are the two peaks in X-ray diffraction. These were the first devices made. It switches okay. Currents could reach 2.8 amps per millimeter in 2017. And then Austin Hickman, who did this work, I'll just show you. The materials were grown by Reed Chaudhary. He grew up very close to where Sir Nilesh is. He grew up very close to Ahmedabad in Gujarat. And he grew these on 3-inch silicon carbide wafers, these structures, and he's basically able to get sheet resistances that are of the order of 650, 630 ohms per square. 340 ohms per square. 300 ohms per square or so. The mobility, the maximum mobility in these is about 800, but the charge is very high, about close to 313 or 2.5 E13. And that's why the sheet resistance is actually very respectable. And in the university, our uniformity over the wafers is not very good. You get the sweet spot in the middle, but you get, not very good on the side. But now I will show you later that the MOCVD methods are being used by companies to try to see whether they can scale this up, because it seems attractive for new generation of nitride electronics. So the process is shown here. We start with this device. We do the regrow, basically pattern, etch down, and regrow the GaN and source and drain contacts, heavily doped with silicon, and then put contacts here. Then we passivate we're using silicon nitride. This is a I gate, but we also make T gates in this sense. We are able to get contact resistances which are about 0.1 ohm millimeter. This is very, very important, as anybody who makes HEMS knows. 0.1 ohm millimeter total, the contact resistance. Of course, the contact to the regrown region is very, very small in terms of its value. Now, the transistor, I'll show you the transistor characteristics, but let me just start off by saying that these transistors exhibit higher breakdown voltage than standard AlGaN-GaN heterostructure GaN-HEM structures. This is the most important things we started with. And indeed, we are able to see that just sort of using an aluminum nitride buffer layer as an aluminum nitride barrier increases the breakdown voltage for similar gate length, similar gate to drain distance, and similar R-ons, on resistance. And that is the most important thing about these devices, that the breakdown voltage is actually pretty good. And we are not, these are very early measurements too. Remember, gallium nitride transistors started in 97, 98. So they have a good 24 years behind them. These have about 5 years behind them. So I think there's a lot to do. But it's starting out at a good place, because that's our main goal. We are dreaming that we want to improve the breakdown and improve the power, and it looks like we're starting at a good place here. The current densities is really nice, more than 3 amperes per millimeter current densities. This is a gate length of 50 nanometer, very short gate length, but the current densities are exceeding 3 amps per millimeter. For about 5 to 6 nanometer barrier, our GM is not very high for this particular device. Austin knows this, I know this. It's 0.6 Siemens per millimeter. We can get it more than 1, maybe even 1.5 in the future. Right now it's at 0.6. We haven't aggressively scaled it vertically yet in terms of the gate length, the barrier thickness, but we will do that. But R-on and the on current is very high. And as you know, these are the bread and butter for any RF device. You need a very high on current, you need a low on resistance. That means your parasitics are low. So now you got a good I times V, a large window of I times V or power. If you can switch it and you can amplify, this I times V, you've got a very large window for power window to amplify now. Now, one of the challenges in amplifying in gallium nitride is, if you make a great DC device, you start measuring it at high frequency, and all of a sudden it just dies because there's electrons, instead of throwing the channel, are in some traps on the surface or buffer or whatever. So that's called RF dispersion. And Austin spent all of 2.5 years trying to control that dispersion. And finally, he's able to now, get a very low dispersion, and he can he's hitting frequencies, Fmaxes in this aluminum nitride platform of close to 250 gigahertz. Actually, this is 240 gigahertz, but he has measured some which are a little bit faster. FT is slightly lower, but Fmax is what we really care about. And you can see that these are actually pretty attractive devices. This one is at a gate length of 70 nanometers, source drain distance of 0.6, with all these things that I mentioned earlier taken into account. So here's some output power. Let me not bore you with the details here, but let me just say that he can bias it at many points and see at what point is he getting the most power out. And when all is said and done, he put this chart together, actually Reed put it together, showing where his data point falls. So he's getting about 2 watts per millimeter of output power at 94 gigahertz using this new geometry of aluminum nitride transistors. Now, there are, of course, from Fujitsu and the DCSP transistors that are, delivering a bit more power at this frequency today, which are also all record numbers. But I must say that I'm very excited about Austin's this approach, because this is very early on, and we know that aluminum nitride can go very, very far with the breakdown and the thermal conductivity in the near future. So we are very excited about aluminum nitride to kind of go into that window of very high frequency and high speed, as I was mentioning earlier, using all its physical properties like great thermal conductivity, very good electrical insulation, at the same time large band offsets, very good scaling capability, etc., etc. And here's a picture of the device that Austin fabricated on material that Reed had grown. And this 94 gigahertz measurement was done by Neil Moser at Air Force Research Labs, because we actually don't have the equipment here at Cornell yet, but we are just getting one, because I think the government was waiting for us to be able to make a device so that they can give us the money to measure it. So, but it was also independently confirmed at Santa Barbara as well as AFRL that indeed it is delivering more than watts per millimeter at 94 gigahertz. So right now there are probably few places in the world that can produce RF transistors that are delivering that much power. I must say that the efficiency is not very high. Maybe I should have mentioned the efficiency at 90 gigahertz is only 10%. It's nothing to boast about. It's really low. That means 90% of it is going to heat. And that's not good. We want to, of course, solve that, and we are starting to get into that problem. Compared to this, of course, that low frequencies, the power is much better. So if you need it for low frequencies, this is going to perform well. But pushing to the top right is where we are trying to head in this particular device, this geometry right now. Okay, so I think I just want to add here that Austin Hickman, when he did the first measurements of this, it was very clear it will probably become important in the future. So Austin started a company, and the name of the company based on this aluminum nitride transistor platform is Socterra. Socterra's SoC stands for System on Chip, and Terra, of course, means for terahertz. And I and Grace are very proud that our students have started a company. We'll see how it does, but it's already has a couple of grants to start investigating scaling up of these transistors to larger areas. Okay, so I will now switch to the second topic. That was my discussion of the N-channel transistors, the new structures that we are working on. I will now switch to a more out there, a little bit more out there work, which is on P-channel and making digital and high voltage CMOS with gallium nitride, all wide bandgap CMOS. And after that, I will go to the quantum systems. So this work starts with this discovery by Reed Chaudhary and Sam Bader in my group of just like in gallium nitride, aluminum gallium nitride, we get the two-dimensional electron gas, so we can make N-channel transistors. Here, what you see is that if you grow on top of aluminum nitride a very thin layer of gallium nitride, it's kind of upside down. You get a very high density hole gas. And this is very interesting because if you look at gallium nitride, a bit of chemistry here, that nitrogen is the most electronegative element in the in group 5. Fluorine is the most electronegative, then fluorine, and then oxygen, and then nitrogen. But in group 5, for 3,5 semiconductors, nitrogen is the most electronegative element. What does that mean? It means that it really wants all the electrons to itself. It just doesn't want to share the electrons. Gallium, of course, is very happy to give electrons, and the clouds of electrons are very large, so they overlap, and therefore electron conduction is very easy. But hole conduction, where you need to empty a valence band to create a hole, that is nitrogen orbitals form the whole bands of the holes, and it's very hard to pull out an electron because nitrogen just doesn't want to give it away. So so as a result, it's very hard to do p-type, and of course we know that that was also the reason why it was so difficult to make p-type gallium nitride, and the magnesium doping, which worked here, is already 200 MeV deep in activation energy. So at room temperature, you get a very small fraction of electrons that can, absorb kT of energy and go there and empty out that whole state so that you get conduction by holes. I mean, the problem was, of course, that important that it garnered the people who solved this problem Nobel Prizes in physics, Professor Nakamura, the late Professor Akasaki, and Hiroshi, Professor Amano. What they found was by taking magnesium doped gallium nitride and doing certain treatment, typically annealing, they saw that they could drive the hydrogen out, and the resistivity dropped by 1 million fold, a million times, from mega ohm centimeter to 1 ohm centimeter. And 1 ohm centimeter in semiconductor electronics means we are in business. We can make transistors, make it contacts, make LEDs and all that. And that immediately sort of unleashed the photonics area, LEDs and lasers within 2 or 3 years. Blue lasers and blue LEDs became possible, and very rightfully they were awarded the Nobel Prize in physics for creating this lighting revolution using gallium nitride. But really the scientific breakthrough was in getting holes to conduct in gallium nitride. All the rest of it was sort of fell in place. Quantum wells and LEDs and lighting was all good, but the p-type was the very, very big difficulty. Now, as you know, that the p-type problem was solved for photonic devices, but we don't have p-channel transistors. Why not? Because it has not been solved for transistors yet, for electronic devices. Why? Because the amount of holes we get in by p-type doping or magnesium doping of GaN is not enough to form transistors. Transistors need way more current than any LED or any laser. And that is why we get a lot of electrons. We make N-channel HEMS, but it is very difficult to make P-channel HEMS. So actually back right when I started as an assistant professor, this was always in my mind and actually many people's mind that can we actually get, just like we're getting electrons in gallium nitride without doping with donors using polarization. If you just turn that logic upside down, you're like, why can't I get holes? I should be able to get holes without any magnesium. Here, of course, they are doing it with magnesium, but the question was, can one do it without acceptor doping? And so we, honestly, in my group and Grace's group, we have been going at this problem for the last 20 years. And we first did it in bulk layers. So we had a graded structures, and we graded from gallium nitride to aluminum gallium nitride. And indeed, that polarization field is able to create a three-dimensional whole system. And this was, used, this we put forward and we demonstrated this back in 2010. And we were granted a patent for this way of doping. And currently, this polarization-induced doping is being used, for example, in deep UV LEDs and lasers. It's being used for very deep UV, short wavelength or very large photon energy photonic devices, sort of the next revolution after visible lighting. But for electronics, what is very interesting is when Reith here at Cornell, we started investigating this structure where we have very thin gallium nitride on top of aluminum nitride. If you remember, this is not very different from the N channel. It's just that the top ALN is missing here. It's just the gallium nitride on aluminum nitride. And if you just look at the energy band diagram, this is a calculation by a self-consistent Schrodinger-Poisson solver. We expect to form a very high density whole gas here. And when Reid grew the structures, indeed, what we are able to observe is with no magnesium doping whatsoever, you can see this blue line here. This is the mobility of holes. The mobility at room temperature, about 20, maybe 25 centimeters square per volt second. Not very high at all. It's actually low. As we lower the temperature, it increases to about 200 centimeters square per volt. Still pretty low, not very high. But look at the density. The density is about 4 times 10 to the power 13 per centimeter square. That is very high. So the product, hole density times the mobility, that is not bad. I can actually make transistors with it. It is not very low. It is not, not 400 ohms per square like in N channel, but it is about 4,000 ohms per square. It's 10 times more resistive, but that's enough for me to start making transistors. Very importantly, the holes, as we freeze it to cryogenic temperatures, if I do magnesium doping, the whole density freezes out. And we know why, because the holes are generated by thermal activation of electrons from valence band state to the acceptor state. This is acceptor doped layer, magnesium doped layer. And indeed, when we look at the slope, it's exactly 160 MeV. That's the activation energy of magnesium dopants acceptors. But if you look at this heterostructure where there is no acceptor doping whatsoever, there is no dependence on temperature at all. Even at cryogenic temperatures of this is shown till 100 Kelvin, but it's down to 10 Kelvin. The whole density kind of almost stays 40-13. There is slight change, just slight change, but it stays around there. Definitely not an exponential freeze up. And therefore, we get this pretty enormous change in resistance, of course, at room temperature decent, but at low temperatures, a very large change. So here's a more close-up structure of this junction. You can see the gallium atoms. You can see the aluminum atoms in this transmission electron microscope image. You can see the word-site hexagonal crystal structure. And indeed, this is all metal polar, by the way, metal polar aluminum nitride, metal polar gallium nitride. If we take the whole density and the whole mobility and we plot it against all other ways of getting holes in GaN. It's just at it has the lowest sheet resistance that you can ever get in this material. And remember, this hole gas is only like 2 nanometers thin, so it's it's a two-dimensional hole gas. Not only that, compared to all other semiconductor platforms, the sheet resistance is actually very attractive. I think the only to be beaten by germanium. So it wins the whole gases here, win not because of mobility, mobility is low, but the high density is the key, and it wins there, and then it's among the best in that sense. And I really like to think of it in this way, that why is it? What is giving us the holes, and why is it temperature independent, right? If you take a hydrogen atom and you say, I want to pull the electron out, right? If you want to do that by heat, then we need to give the electron 13.6 electron volts. That's the ground state energy of hydrogen atom. That means you need to heat it to 15,000 Kelvin. Of course, that's very high temperature, but you have to go somewhere, maybe 5 kilometers under the surface of the sun or somewhere, and you reach that. So it's very high temperature, or in some stars or somewhere, but not under normal conditions. But you can easily take a hydrogen atom and put 2 electrodes around it and apply a voltage, and you can tunnel that electron out at 0 Kelvin. There's no problem. So it's basically kind of a field ionization. It's electric field or tunneling ionization instead of thermal ionization. And this was, of course, explained by long ago during the discovery of quantum mechanics itself. And this is exactly what is going on in the whole gas. What's going on is the nitrogen atoms are holding on to those electrons, and if you want to release them, you put some magnesium and you have to heat it up, or you have very few of them ionized. But the moment we use this heterostructure, this huge electric field is pushing electrons out from here, field ionizing them and emptying out the valence band states, and you're getting the holes. So that's very exciting. Right. So we then immediately made transistors with it, because we have a whole gas, we can make ohmic contacts, we can make gates, and we started scaling the transistors. And back in 2020, Kazuki was able to hit about half an ampere per millimeter, 450 milliamp per millimeter, or half amp per millimeter at a gate length of 120 nanometers in a p-channel device. And the FTF maxes at that time were about 20 gigahertz. And it kind of is, has a nice IV curve and all that. And today, Kazuki is able to get about 1 ampere per millimeter in a p-channel gallium nitride transistor, and FTF maxes of about 40 gigahertz. So we are starting to kind of get the p-channel to work in gallium nitride. I should say that we are not ashamed of showing the data now, because p-channel transistors have always been very bad, but now it is possible, and I think it has a bright future. And it's improving continuously as we work on this layer structures. So I will leave it at that. I showed you the big dream that we need N-channel, we need filters, we need p-channel transistors. The p-channel transistors are somewhat at their infancy, but its potential is enormous, because when you combine the N and P, you can get a wide bandgap CMOS, and you can do a lot of basic level digital electronics to assist the gallium nitride RF front end. And I think that's great, because you can do it with silicon, but you can also do it with GaN. And one of the beauties of GaN is it survives 500 degrees C. These transistors are going to work at high temperatures too. And that is very, very important point about being able to make transistors with both N and P with the wide bandgap semiconductor, where a narrow gap material like silicon may face a lot of problems at high temperatures. Okay, I know I have not kept track of time, and I hope I'm not boring people now. So I will start ending the presentation with the third part, which is to me and some of my students, especially students who love to do physics, this is very exciting new area. Basically, it's limited by our imagination when we start integrating superconductors with gallium nitride and aluminum nitride, and start steering some ideas towards combining the microwave the microwave capability of gallium nitride and RF capability of gallium nitride to start shrinking quantum computation systems like qubit systems, and at the same time looking at new ways to for quantum communication as well. So both areas can be addressed using this sort of approach, but it's really based on the GaN RF platform, and that's an important one. So. And this work is done primarily by my PhD student, John Wright, and Frank, Guru, and Betul have participated in that, but it's really almost predominantly done by John Wright. As we know, the nitride semiconductor family is expanding. I, with my students, wrote a review article on that in terms of material possibilities. Of course, gallium nitride is the primary player, with silicon and germanium being N-type donors, magnesium being an acceptor, and gallium and aluminum and indium also playing a role. But we have this whole zoo of elements in the left end, which are transition metals, such as niobium, such as titanium, such as scandium. These also form amazing nitrides, and they have very exotic and very interesting properties. And many of you are probably well aware of it. But let me show you what we are trying to do. So you can categorize them. They have the semiconductor nitrides. You have metallic nitrides. And these metals are also at low temperature superconductors. Niobium nitride is a prime example. It is a superconductor with a TC of 17 Kelvin. It is, I mean, of course, not room temperature. But it's enough to be able to be attractive for many applications. There are magnetic nitrides. I won't talk about that. If we start adding scandium and the first transition row to aluminum nitride, it also becomes ferroelectric, and that's very, very exciting for, I think Nilesh mentioned AI and ML, right? Now, ferroelectric gate is very exciting because you can have a non-volatile transistor, non-volatile logic device. And to me, nothing will make me happier if I could do it than if I do it with the nitrides. Right? So we're trying to work on that. But so niobium nitride nicely is almost lattice matched to aluminum nitride and GaN, and that's very, very exciting. That means you can create single crystal structures of GaN and NBN, or aluminum nitride and NBN. Similarly, scandium, but I won't talk too much about scandium. Just one slide on scandium. This is what I was mentioning, that if we start adding scandium into aluminum nitride, these are ferroelectric loops. And you can basically, if you use that as a gate of a transistor, you can make a ferro-FET, which is a non-volatile transistor. Now that's very interesting because it's a hybrid of both memory and logic. Non-volatility gives it memory, and logic is, of course, is a transistor, so you can switch it. And with this combination, you can do deeper level neural nets, etc., because you have removed the bottleneck between memory and compute, and which is a big bottleneck in which forbids some of the applications. Now that's a dream, of course. This material was just discovered in 2020, basically 2019 December. That this material is ferroelectric, and this is very exciting because this is sitting right up on top of GaN, with which we can already make amazing transistors. So I'm very excited about this, and we're pursuing this area right now. Just one slide on this. But let me move over to the superconducting aspect and quantum. And this is where I'll kind of few slides, and I'll end the presentation and open up for discussions if you have questions. So what we are really doing right now is developing the material platform to make two things. One is very, very high efficiency single photon detectors for quantum communication and applications in quantum communications. The second is we are developing fully epitaxial Josephson junctions to increase the coherence of qubits. Coherence is one of the big killers, with one of the reasons why we cannot have 1 million qubits today is because we can have 1 million qubits, but every qubit has to talk to everyone else when you entangle them. But every qubit has a certain coherence lifetime. The world record right now is about a millisecond. That's, people in Princeton are saying it's a millisecond. Nobody has seen the data, but hundreds of microseconds. That's how long one qubit survives. But if it has to be entangled with another one, and it only survives 100 microseconds, by the time information has gone there and come back, it's dead. So we can only entangle hundreds of qubits now, and it can't entangle large. Our dream is if we create the qubit out of a material with very, very few defects, it should have a very high coherence. And that's what we're dreaming about. I mean, we don't know it, but it's not completely logical to think of it that way. So we are exploring how to make those qubits, how to make those Josephson junctions now by exploiting the nitrides. Here are some papers, but I'll kind of take you through them. The qubit idea, I think, is very, most likely most people know about it, but I'll just mention it. The qubit idea is, it's a very strongly coupled light and an atom with two levels. If light is bouncing back between two mirrors, it's so strongly coupled to an atom with two levels that sometimes it gets absorbed, sometimes it gets emitted, it's very difficult to say where is the energy. Is it in the atom or in the light? And that's entangled. The two are entangled, right? And then this two-level system is the qubit then. Now that's the atomic way of doing it, and there are some people doing ion traps and all that for qubits. But the most advanced one right now, according to me at least, is a circuit-based one, where that photon is a microwave photon, typically about 10 gigahertz or 8 gigahertz frequency, and so that has a large wavelength, and the cavity is made out of a superconducting wire. So this is a transmission line made out of just like RF transmission line. And you cut these at two ends, and those are the mirrors. So the wave will be basically form a standing wave in between there, and the microwave photon will just slosh back and forth here. What is the microwave photon? Honestly, it's just the current, right? So you don't want any dissipation, and therefore the current has to be in a superconducting wire, not in a normal metallic wire, because otherwise the loss will kill it. One photon is going to be dead very fast. So once you freeze the temperature, go to superconducting, there's no loss. So the photon will bounce back and forth forever. So, and that is true. In fact, the cavity Qs here are very, very high. They are not limiting anything right now. What is the two-level system? The two-level system is a Josephson junction. Basically, it's a superconductor, insulator superconductor tunnel junction. And the Cooper pair tunnels across it. And that gives you that two-level system. And with a little bit of tweak of current and voltage, we can adjust the energy of the two-level system so that it exactly matches the photon energy at 10 gigahertz. And now that photon energy will be either swallowed by the superconductor, or it will be either in matter. The energy will be either in matter or as a wave. And that's your qubit now. That is one qubit. Then you make 100 of them. Here about 100 miles from here, we have IBM. They have made 130 qubit. They're exactly using this technology. Their tunnel junctions are made out of aluminum, and their lifetime is about 1 microsecond, which is why they're really frustrated that they can't improve the lifetime for its lifetime. So they can make this beautiful quantum computer, but it has only 100 qubits. Can't do much with it, So how do we know there is one qubit? You need to have a single photon detector. That's of course used in quantum computation and quantum networks, but of course it's used much more in radio physics and radio astronomy. Single photon detectors are made out of a single, superconducting wire. I don't want to go through all the details, but just one of the things I can say is that if you have a superconducting wire that is narrow enough and one photon hits it, the photon actually excites across the superconducting gap, just like an electron hole pair in a semiconductor, and it makes that region non-superconducting. So that's a normal metal. So when you're measuring the resistance of this chunk of superconductor, it is 0 before the photon hits. The moment the photon hits, you have a finite resistance. So there's a voltage drop across it. And after some time, it heals, and it goes back to superconducting. So you can count a voltage pulse, and that's one photon. Single photon detector. This is not an old device. This is a 21st century invention. Only this is the first paper, 2001. So what we are doing now is we are growing by molecular beam epitaxy. It can also be done by MOCVD. We are growing niobium nitride on top of aluminum nitride. It's a flip upside down here. So we grow single crystal niobium nitride. And its superconducting transition temperature for this one, this is grown by John Wright. It's about 12 Kelvin. And here's that pulse I mentioned. One photon is hitting that niobium nitride wire. It's been fabricated into a very thin wire. One photon hits it, and you can see there's a 5 nanosecond time. This is not the best, by the way. You can make it much smaller. You can have a picosecond resolution. But nevertheless, you can get 100% photon counting rate, meaning if I have single photons coming, I won't miss a single one, so there's that single photon, and this material improvement is very useful to make it better. More importantly, once you get that voltage, we can connect it to a GaN HEMT that is built directly on this chip, and we have an amplifier too. We can do logic with it. We can do an RF amplification based on the if say Nilesh sir's satellite tells me I got the photon, now I want to send my signal to my base station that, here's the news, maybe, something's going to happen. So I can have the RF integrated directly with the structure in the same material platform. That's very exciting. What John has been finding is he's able to also discover a new phase of niobium nitride. Now, this is kind of very exciting, and I'm sort of sorry I'm showing that in the very end. But niobium nitride is almost a 100-year-old superconductor. But as John started growing this at very, very high temperatures, he discovered a new phase, and this is not yet published. This is a hexagonal phase. What do I mean? NB2, and the crystal is hexagonal. And that means you can grow aluminum nitride on it, and aluminum nitride is a hexagonal crystal. So you can grow nominally perfect niobium nitride, aluminum nitride, and niobium nitride on top. And you can make, and these are very, very smooth surfaces. And then you can see, here's the Josephson Junction now. Now, Josephson Junction is the heart of that qubit. I showed you earlier that niobium nitride forms a very nice superconducting channel, transmission line. And here's the atom, so to speak, of that junction. And here's the first Josephson junctions that John is making now using this nitride platform. Our dream is to kind of combine this Josephson junction and the niobium nitride superconductor and the GaN transistor or ALN transistor to make a fully integrated microwave qubit, because currently microwave qubits are getting their RF power from outside, from another chip with some filters and circulators, all that. We think we can put it right on this because we can make a GaN RF amplifier at 10 gigahertz with not much problem. Our problem may be in heat or other issues, but definitely not in getting the power. That's not an issue. Our challenge will be to attenuate it and make only one photon out of it because it can generate a lot of power, right? And then to decouple the heat because, unless you have very high PAE, the heat is, but that's what we're dreaming about. We are trying to shrink all these components, which are currently made out of different circuits, different things, just like in classical computation. I showed you the chart where, filter is made of one thing, PA is made of one thing, this is made of one thing. We could combine all of them with the nitrides, and we are really dreaming of doing that in the quantum computation arena as well. So, okay, so this is the first device, and we're still far from that dream, but we're going in that direction with the nitrides at this point. Here's a proof of principle. In fact, one of the first qubits was made out of the NBN, ALN, NBN structure, but it was not epitaxial, so its lifetime was very low. But this is from Nakamura's group in Japan. One of the first qubits that was demonstrated used this structure, but it was didn't have a very good lifetime. And if you can see the frequencies were 5 gigahertz or so. Here's an example of a few more things one can do. This is a collaboration with ETH in Zurich, where the qubit is integrated with the aluminum nitride bulk acoustic wave filter, and for selecting the frequency at a particular wave. So let me see. I'm probably reaching the end of my time, so I will hurry through here. Show you that we have started integrating the transistor with the superconductor now, and the GaN transistor with the niobium nitride superconductor is integrated. And when we start integrating these, what we are seeing is also very interesting, nice phenomena. For example, the 2D electron gas of the GaN transistor can show integer quantum Hall effect, very beautiful integer quantum Hall effect, very sharp, integer steps. And at the same time, at a high magnetic field, the superconductor, which is NBN, niobium nitride, it's still superconducting. Typically, superconductivity is destroyed in a magnetic field. But because of the crystalline nature and the perfection of the crystals here, very high interface quality, they can both survive. So I think that's very exciting. We are kind of starting to dream that in just like power electronics, lighting, power amplifiers, we think gallium nitride can also help to shrink the currently warehouse shaped quantum computers into very small chips because of its integration. Of course, cooling and other things we don't have solutions to that, but as far as the material platform goes, it's very exciting, honestly. So with that, I will end the presentation. I still feel that we are just at the threshold of very big things in gallium nitride. We are dreaming big, and most of us are dreaming big, but there's a lot more to come. Sort of looking at the history, gallium nitride was known in 1960s, but only when p-type GaN was discovered in 91, the LEDs and lighting took off, right? The 2D electron gas was discovered in 92 by Professor Asif Khan. And then transistors started becoming available around 2000. Polarization was understood in around 2000. commercial GaN HEMTs just started appearing around 2006, 2007. We are very excited. The whole gas has started appearing, and now ferroelectric nitride, superconducting nitrides, etc., are appearing. So I am very excited about the future of this area. And I'll end my presentation here. And I don't know whether I lived up to what I was saying is a big dream, but I think we are very excited about taking nitrides into all these directions that I mentioned, and I hope it gives you an idea of some of the work that we are doing and many other groups around the world are also doing. So with that, I'll stop here, and I'm very happy to discuss and take questions and hear your comments or suggestions as well.
Thank you,
Thank you,
Dr.
Professor
Jana.
Jana. Now,
Yes.
session is open for the questions. May I request to all panelists, please raise your queries. Yeah. Okay, we have a question here, sir, please.
Yeah, is this typed, the question, or should I?
First, we will ask from here. Later on there are some question on YouTube. We will discuss it.
Okay, sure. Yeah, go ahead.
Hello, am I audible? I'm Dr. D.S. Rawal, works here at SSPL on gallium nitride HEMT technology. And my question is related to gallium nitride HEMTs only. How do you see future of these GaN HEMTs using aluminum nitride as a substrate? Because recently, last year, there is a report from Fujitsu where they have reported very low defect density during growth and 15 watt per mm of power at X band.
Yeah.
Anytime sooner, are aluminum nitride substrates replacing silicon carbide?
Yeah, thank you, Dr. Rawal. This is a very exciting question, and thank you for asking it. In fact, you are right. Fujitsu Labs, as you know, the hemp was discovered in Fujitsu, long time ago, and they have kept going at it. In fact, they back in 2012, 2013, when we published the first paper on aluminum nitride, they were the first company to email us immediately and said, how did you grow that channel? They knew that, and they started it very early. So your question about the substrate, you don't need to have an aluminum nitride substrate. You can do this on silicon carbide. You can also do it on silicon. Of course, then you have to pay a bit more thermal penalty. But you need to grow a thick nucleation layer and then a thick ALN buffer layer. That's all you need to do. I mean, so you don't need to switch to ALN substrate completely. You can do it on silicon carbide. And in fact, all our RF data that I showed you today and all the Fujitsu data Fujitsu is showing bulk ALN too. I mean, I understand what you're asking, but silicon carbide is going to be a very strong contender, and it's a great substrate. You don't really need to go to bulk ALN. Bulk aluminum nitride is, of course, that's the completely high end, and it's very difficult to get these days. But silicon carbide can still, be enough for developing the ALN based substrate. And indeed, the power output that was shown by Fujitsu, that is not at a very high frequency, by the way, but I think you said X band, right? I mean, and that's already very, very impressive, I should say. So yeah, it's very capable, and I think on silicon carbide, it will be great. It can maybe even be done on sapphire, but then you'll have a lot of thermal problems.
Thank you. Thank you.
Yeah. Next question. Yes. Yes, sir. Dr. A.K. Gar.
Sir, I'm Dr. A.K. Gar from SSPL. Actually, my experience as far as aluminum nitride is concerned, you see, if the total substrate is of aluminum nitride, the thermal management will definitely be a big game changer. But so long as you're using a silicon carbide as a substrate and then using the aluminum nitride as a buffer, as far as the thermal management is concerned, it's not good. To my understanding, it's not solving that thermal management very well. But if you, as Dr. Rawal asked me about the substrate of aluminum nitride, this particular work in 2007, a 2-inch silicon aluminum nitride substrate was demonstrated. But till today, the state of the aluminum nitride substrates in the world has not improved to that extent that one can think of having a, you replace it as a substrate for silicon carbide. To me, it looks like, as far as aluminum nitride, so if substrates are concerned, it is going to take another 10 years, maybe, to reach to some level where it can replace silicon carbide. But as far as thermal management is concerned, I am still not convinced that whether putting a buffer layer of aluminum nitride thermal management can be handled in the present scenario.
Right. That is a very good point. Thank you again for asking and making this point. So there are two aspects, as you very correctly point out, and I think Dr. Rahul was also pointing that the thermal conductivity of ALN is one thing. Thermal conductivity of silicon carbide is actually better than aluminum nitride, but the big problem is the interface. You have a thermal boundary resistance between the two, and that is what can basically destroy any advantage that you may have had from aluminum nitride. Now, two aspects to it. Fundamentally, we are exploring the interface thermal conductance, thermal boundary resistance right now with very careful measurements of these HEMS, with comparing them to standard GaN buffer layers on silicon carbide. And already we can see about 30 to 40% improvement. But I think you were right. It will take some time to really, make sure that that is real, and you can see the improvement in PA and all that. That being said, the substrate development has been reasonably rapid, not because of electronics, but the substrate development is being driven, like everything in nitrides, by photonics, because UV photonics is becoming very important. Currently, for LEDs as well as for lasers, people are starting to, mainly for LEDs, people are starting to switch over from, they're using sapphire, but they're also, Santa Barbara and a few other companies are looking at growing on silicon carbide. So substrate development is a painful thing. We are living the pain that people had to, develop gallium nitride substrates or templates on sapphire or silicon carbide through the 90s, through the 2000s, right? You were right, there was one demonstration of ALN on silicon carbide early on, but people never made transistors with it. As I was trying to say, in my opinion, ALN on silicon carbide has a thermal boundary resistance that is going to be limiting, but it's not going to stop the fact that we can already see that the thermal boundary resistance is at least 34% lower if we use a ALN buffer layer compared to the GaN buffer layer. Now, these are advantages that may or may not be a quantum leap compared to what currently exists, right? On the other hand, if you go to bulk aluminum nitride, which is a very difficult thing, then you remove the thermal boundary resistance completely. Now, but then that is another challenge. We don't have bulk aluminum nitride substrates right now easily available. We have 2-inch wafers, very hard to buy. But then you lose the advantage of silicon carbide, which has 6 and 8-inch now. I believe personally, based on doing the numbers and doing some modeling of the thermal boundary resistance and phonon conductivity across the interface, that ALN on silicon carbide is going to be superior than GaN on silicon carbide, in my opinion. But we will have to see, because that's just an opinion till it's proven experimentally. So, yeah.
So, yeah, please come here. We have one more question here.
Good morning. I'm Dr. Mamta Kharija, working in the area of quantum devices. So I just had one small query. You had mentioned the niobium nitride based superconducting nanowire single photon detectors. So have these detectors been actually fabricated at Cornell? And if so, what are the dimensions of the meander structure? Or
Okay.
Yeah.
Yeah, thank you for asking this question. So let me see if I can bring that chart up again. Let me share. Yeah. So if you see this particular device that I'm showing you right now here, this is actually not fabricated at Cornell, but at Yale University by Professor Hong Tang. He is our collaborator, and we have a joint project on single photon quantum systems with him. So we are growing, and we are and they have fabricated this nanowire SNSPD. That being said, my colleague here, Professor Greg Fuchs, he has currently fabricated SNSPDs for some other purpose here at Cornell. And they are, I think Greg's device is a little bit better. This is slightly old. You can see the dimensions here. This is a SNSPD with a nanowire width of about 20 to 30 nanometer, and it's very long, and hopefully the geometry is visible in this slide to you. Hopefully this answers your question. So we have CNF, Cornell Fab, fabricating these, but this particular device is 2 years old and fabricated at Yale University as a joint project. You probably know that Yale has a very strong quantum computation and communications program. So they wanted to investigate the materials we were using, we were growing, and currently these are being fabricated here as well.
And what were the efficiencies which were achieved for such detectors?
Excuse me. So if you don't mind, if you drop me an email, I can send you the paper, and that way it will be a little easier for you to maybe calibrate against all the metrics that you may be of interest to you. So please, if you don't mind, just drop me an email and I can send you information.
Sure. Thank you. Thanks a lot.
Sir, is there any question from the panelist?
Yeah. Shall I?
Yeah.
So thank you, Dr. Jaina, for a very illuminating and exciting talk where you took us to the journey of this nitride semiconductor. I have one query. You mentioned in passing about this microwave photons. Basically, we are initiating a program related to quantum radar development. Now, to start with, we are starting with optical photons and all. But finally, if you have to achieve some results, you have to move on to microwave photons. So, how far do you see the maturing of this technology of having a microwave photon generator as well as again detectors for that?
Got it. Yeah. Thank you, Mr. Desai, for a good question. And please also correct me if I misunderstood your question. But I think what you are asking is for communication, you have a choice of optical or microwave photons. And of course, when I'm making a cell phone call, I'm using microwave photons. But if I am, sometimes using optical fiber for my email or something, then it's going at light in an optical fiber. So you are asking about the quantum part of it, is that right?
Yeah, means how to generate a microwave photons.
I see. Yeah. So
technology related to that.
Yeah.
Because
So this
in radar you transmit a signal which goes to a place and it comes back.
Indeed, indeed. So I think the big challenge, in my opinion, the big challenge with microwave photons in the quantum arena is that there is way too much absorption because the energy is so small, milli-electron volts, that every atom or molecule in the gas or the air that it collides with can cause a vibrational mode or something like that. On the other hand, a light photon, optical photon at 1.55 micron or something, if you have a single photon, you can transmit a very long distance and it has fidelity and it goes very far. But microwave photon generally, because in any matter there are vibrational modes and all that can absorb it. So we lose single photons very easily in the microwave. And that is why for communications with microwave photons, I think personally it has to be done at low temperatures through superconductors. Anything else at a single photon level is going to be very hard. So I think for communications, quantum communication on chip or inside a quantum computer or maybe even inside a data center, there the microwave photon can be used in the quantum domain. For generating it, I think in the end, everybody will always use, I think, in my opinion, a HEMT. And currently, all quantum computers are using, all microwave quantum computers are using gallium arsenide LNAs and LNAs in one end, and they're using the gallium arsenide cryo-cooled for generating the 10 gigahertz photon. I think that can be done with gallium nitride too in the future. Of course, it needs a bit more work, but it can be done. But as far as transmitting, I feel it is probably very hard to go in direct, air atmospheric communication with microwave photons for quantum computation. That probably the link will be you do your quantum computation with microwave, you then you have to have a converter. You have a single microwave photon, you have to convert it into an optical photon. And that's something my colleague at Yale, Hong Tang, who's my collaborator, he's doing. He is using my favorite material, aluminum nitride, to do that. He has this thing called the infinity resonator, and he uses the piezo acoustic wave property of the microwave and to convert it, and using the optical nonlinear property to make it a visible or a optical photon. So you kind of up convert it. So it is very hard to do it at a single photon level, but he has succeeded with about 40% efficiency at this point. So it's, yeah, that's my opinion. I hope I'm answering your question there, that to go to free air or optical fiber, one needs to have that, impedance from microwave to optical at some point.
Thank you, Dr. Jinan. One more last question. This you mentioned, one of your slide was mentioning qubit of microwave kind. And here we are also working on something called quantum memories. So whether there you see any role of this particular, what you explained today of nitride semiconductor?
Yeah, so a quantum memory is a very interesting thing. I think that's very, I'm excited that you're, that's one of the areas of research for you. Quantum memory is something that many people are trying to figure out how to make it. It's very difficult, and primarily because one of the things that people have asked me whether we can create is, if you saw, we were talking about these superconducting Josephson junctions. If in the Josephson junction the barrier layer is a magnetic material, then it has a chance of having some sense of a memory. Some people are looking at that, but honestly, I think it's very early at this point about the quantum memory. But it is. I should, sort of say that I'm definitely not an expert in that, but I know some materials that people have asked for. For example, they're saying, can you add a little bit of manganese, which is a magnetic ion, into the niobium nitride? Because that will give me a chance to make a quantum memory. But I don't quite completely grasp why is it a good memory or bad memory. I don't know that yet, honestly, by myself. So it is of interest. Many people here are thinking about it. Some of my colleagues are thinking about it. So if there's more thing you would like to hear from me, I can definitely find out and let you know.
Yeah. Thank you.
Any more question from the panelists? So we move on to the YouTube questions. We have one question.
Janesh, this is
Yes, sir.
Rajesh Sharma.
Yes, sir.
Can I just?
Yes.
So,
Please go on.
it has been a pleasure, as always, listening to Professor Jaina. I had a couple of distantly related questions, and first one is that what about gallium oxide?
Yeah, thank you.
Second is
yeah. No, go ahead. Go ahead. Yes, I can.
And so I'll just put another question. I had three, but I heard one of that is already answered. And the second thing is that in silicon carbide technology, we are hearing about silicon carbide bonded to aluminum nitride substrates, which are more cheap and easily available. Any possibility of using this for nitrides, not primarily for aluminum nitride, but nitrides in general? Thank you.
Yeah, thank you, Dr. Sharma, and also very happy to see you again. And so, first question: gallium oxide. I really feel that gallium oxide has to find a place for itself. It is a very good material, honestly. It has problems with thermal conductivity. Its mobility is not very high, but it has a close to 5 electron volt band gap. So I think it is very early right now to either say what is it going to win in or what is it going to lose in. So it needs a bit of support and research, because in my opinion, the first area would be something very simple where it can actually have an application, high voltage Schottky diode, something very simple. Because we have bulk substrates, you can make, in principle, very good high voltage Schottky diodes with it. And probably if it can offer in the market, I know this is not scientific answer, but if it can have a foothold in the market, I think it will find more applications in the future. So That's why, because it has one of the beauties of the oxide thing is, what's the worst that any material goes through? It oxidizes, and gallium oxide is already an oxide. So it is definitely going to have a lot of chemical resistance to many things. And its high breakdown voltage means that there may be some niche high voltage applications where it can get in, where maybe heat is not the problem, maybe low current, but very high voltage, rating. So once it gets there, then I think some transistors can start, getting in, and it has to build on that. So I'm honestly very optimistic about its future because it has a large gap. Ultimately, its physical, that should. One of the challenges, though, we don't have p-type, right? So the entire band gap can only be exploited if you have a p-n junction. Otherwise, you will only, a Schottky barrier height will be exploited. But I think nevertheless, a Schottky barrier height, which is 3 eV or 4 eV, now that already there is no other semiconductor with which you can do that. So that is already a game changer if it can be, introduced. The biggest challenge with it that is it has very stiff competition from silicon carbide and gallium nitride, very, very stiff competition. So that's where, and those materials are not sitting around doing nothing either. So they are getting better every day. But I think for young people, it's an exciting area of research, and I always support young people to look at it, and because they may discover new things in it. So now your second question, hopefully that answers. That's just my opinion, but of course we'll see how things go. The second question was silicon carbide bonded to aluminum nitride, and is that aluminum nitride sputtered, or is that an epitaxial, or how is it? Is it highly crystalline, or do you know? Meaning that layer? Yeah.
I'm thinking of standard ceramic aluminum nitride with a good.
Okay. So I see. So if it is ceramic, then typically it would be maybe polycrystalline, I would imagine. In which case, I think growing a nitride on it may not be that easy to get a high mobility and all that, because if it's polycrystalline, you may get a little lower performance. But I think unless one tries, it's hard to say, because even when we nucleate aluminum nitride on silicon carbide, it already has a lot of defects. And still, magically, when we start doing epi and increase the temperature, it recovers and becomes more perfect, and mobility gets better. So I think one can try it, but I would be a little worried if it is not highly crystalline to start doing transistors with it. Yeah.
Oh, my point was for the back end, for thermal management. I'm not talking about, say, my point is that I have a very thin silicon carbide pasted on or say bonded to a aluminum nitride substrate, and then use that silicon carbide for all as substrate. So
I see.
Just for yeah.
Probably then, meaning you are saying not from the point of view of trying to make an active device on it, but actually using it as a spreader or something like that. Probably, yeah. I think that may be I mean, silicon carbide is a good heat conductor, very good heat conductor, honestly, right? And I think here you can also use that for sure, right? Yeah. Okay. Sorry, I don't know whether I answered your question there, but I think that's
it's okay. Thank you. Just came to my mind. Thank you very much.
So we move to next questions from YouTube. We have one question from Shailendra Singh. Have you designed any RF power RF amplifier using the aluminum nitride / gallium nitride substrate? Number 2, is this process easily compatible or integrable with the existing GaN process?
Yeah, thank you, Shailendra, for this nice question. So when you say, have we designed a PA, I don't know whether you mean like a full mimic or not, but I did show you some of the data, and they were discrete devices. They are not fully, there's no power combining, there's no, mimic design around it. It's just a discrete device which is measured measured. Of course, it has the GSG probes and all that. It has RF in and RF out, so it's measured that way, the power amplifier. And the data I showed you, which is at 94 gigahertz, about 2 to 3 watts per millimeter, maybe not a whole lot more than 10% efficient PAE at this point. That's not a mimic. It's a PA. It's a discrete RF amplifier. I hope that answers your first question. And one of the reasons we have not done it is because it's very new, and we are exploring and in fact mimic the circuit design of the mimic and all are happening gradually, and it will as we improve the device also. I think sorry, Shailendra, I missed your second question.
Yeah, second question is that is this process easily comparable or compatible with the existing gallium nitride process?
Yeah, that's a great question. So the major difference between the my first answer is absolutely. It is we are using exactly the same process as a GaN-HEMT process for making this ALN-based PA. It's basically a nitride after all. The major difference is in this HEMT on metal polar, you cannot make the transistor if you don't have regrowth. To connect to the 2D electron gas, we need to etch down and we need to regrow N++ GaN. In AlGaN-GaN structures, you can put a metal directly on the AlGaN and thermally anneal it, and the metal diffuses in and you can form ohmic contact. But aluminum nitride is a different beast because it is very, very insulating, and it is, as was just discussed, it is also a ceramic. It doesn't allow any metal to diffuse through it. So it is very difficult to make ohmic contacts to the 2D electron gas through the aluminum nitride. So we have to etch it and do the regrowth. As long as you have the regrowth, the entire process is the same as a standard GaN-HEMT.
So third question is why is this silicon carbide lowest layer still required? Means maybe he's asking about this as a substrate, silicon carbide.
Yeah. So it's not like it's still required, meaning you can swap it out for silicon or aluminum nitride or anything else, but at a size of 6" and a very high thermal conductivity, that is the only material available. So the two boxes that it ticks is it has a large area and it has good very high thermal conductivity. Plus, it is very, very closely lattice matched to aluminum nitride. So the defect density in ALN can be very low. Silicon carbide is more lattice matched to aluminum nitride than it is to gallium nitride. So with aluminum nitride, we can keep the defect densities even lower than on silicon carbide than if you grow GaN on silicon carbide. So that's the other point.
We have next question.
Yeah, go ahead.
We have next question from Mr. Sandeep Chaturvedi. He is asking question about your W band results of aluminum nitride HEMT. What needs to be done to come around the problem of this lower power and very small gate length you are using, and how to improve the efficiencies?
Yeah, great question. Thank you. I mean, this is, of course, is what's keeping at least a few of the group members very busy. And it's, what is the big problem? That's the first question, right? So I would say the big problem is that not enough time has been spent on it yet. So the efficiency always, improves as more people work on it and, figure out how to passivate, how to do this, how to do that. Currently, there are only two groups in the world which are making a HEMT of this kind. One is Fujitsu and one is us. And we hope that there are more people in the near future because, I mean, you can make a HEMT with it, which is probably as good as a GaN HEMT, sooner or later. But then going beyond the GaN HEMT, we need to, it will definitely require a slightly different passivation and all that, which we're working on. So that's really the big problem, that not enough work has been done yet, and this is a very new thing. And when it's new, it has to start somewhere, and it just falls at W band at 94 gigahertz. It's delivering only 2 watts per millimeter at 10-12% efficiency. Whereas if you look at the metal polar, I mean, Raytheon is getting about also 3 watts per millimeter at 15% efficiency. But the nitrogen polar GaN HEMT with Professor Mishra is doing they are getting quite a bit more power, 7-8 watts per millimeter at close to 30% efficiency. But I think, this is also a question of age of this technology, how much work has gone into that. So it will improve. I think it will improve very fast, honestly. Yeah.
Yeah. Uh, Yeah, Dr. Renu Tyagi from our lab wants to ask one question about GaN on diamond. I also have one question I will ask later on.
Sure.
Yeah, I just want to ask whether you're doing some work of GaN on diamond, and how, if not, or what is the scope in future? How do you see it comparing GaN on silicon carbide to GaN on diamond?
Yeah, I mean, thank you for this question. The let me just wear my semiconductor materials person hat for a second. If I had very, very good diamond, I don't need gallium nitride. So I will make a transistor with diamond. It will beat gallium nitride, right? So what I think you are asking is, for thermal dissipation, is diamond a good option? Absolutely, why not? For heat dissipation, you have to deposit the diamond or you wafer bond the diamond. I mean, the company out of Cornell was doing wafer bonding, diamond wafer with which they buy from Element 6. They'll wafer bond to a GaN HEMT, which they release, and then they wafer bond it. I felt that was a great idea, but when you look at the data, the thermal boundary resistance was killing it. The heat, once it hits the diamond, it goes beautifully, right? But a lot of acoustic photons which carry the heat get reflected because there's a huge thermal boundary mismatch. So on the other hand, what is very intriguing is when people are depositing polycrystalline diamond, it actually seems to be doing something good, So it's not very big change, but it's doing something reasonable. So I feel people should continue exploring it and look at it. But let me put it this way: I'm pretty happy I'm not working on that myself, because growing polycrystalline diamond or nanocrystalline diamond is pretty hard on GaN, and I know that few groups have done excellent work, but I don't work on that directly. What I'm really looking out for now, though, is what are diamond transistors doing, because they are getting better, And when you have a good diamond transistor, why do you need anything else, right? So because your thermal conductor is awesome, and I saw the latest P-channel diamond transistor from Japan, they are getting close to 0.2, 0.3 amps per millimeter. They're starting to doing RF measurements. So I am watching that very, very carefully, because that that is going to be a really, really interesting development. Of course, the big challenge there, like in GaN, like in ALN, is doping. If you can't dope it, you don't need to dope for the channel. You only need to dope for the contacts, And because you can always create a channel with field effect, but you need the contacts, right? So I think that is a very exciting procedure forward. For GaN HEMTs, I think diamond will continue to be explored, and probably it will have some advantages from the thermal perspective. But what I'm trying to say is I haven't seen a big change with diamond yet. I haven't seen it, but I wouldn't be surprised, but I haven't seen it.
Yeah, but last week I had a conversation with Professor Martin Kubal regarding this same topic. He said that on silicon carbide aluminum, this algan GaN HEMT on silicon carbide has limitation due to this thermal boundary, and it cannot be used in space. He was citing the limitations. One of the limitations is the thermal issues. Still, they are so huge that they are not deploying in space. And the
Yes.
second issue, he discussed that and due to this radiation, there was point defects in the silicon nitride and the passivation, and that creates a big problem. Someone has to look into those issues.
Yeah.
So this was just a discussion I was doing.
Actually, Yanis, in case I'm not pessimistic at all about diamond. What I wanted to say was that if your question was compared to silicon carbide, is diamond a better substrate? I would say currently not a better substrate,
Yeah,
primarily
currently it is
because
not.
I can't get more than 5 by 5 millimeters, so that's the
Yeah,
problem.
yeah.
Yeah. But in the long run, I mean, diamond is the king of all semiconductors. It's the prince in waiting. It's a prince in waiting. You know, so.
Okay. So next question from Mr. SP Mittal SEC, that thermal conductivity for aluminum nitride is 50% higher than gallium nitride, but at the same time the contact resistance for aluminum nitride is also 50% higher than gallium nitride. So how the higher contact resistance is going to be taken care of in order not to nullify the impact of higher thermal conductivity? Basically, it's process.
Yeah, great question. Thank you. So actually, the contact resistance would be high if we try to make the contact, through the aluminum nitride. But as I mentioned a little bit earlier, that we remove the aluminum nitride and we regrow it. So then the contact resistance is actually almost this same as the lowest contact resistance ever reported with no aluminum nitride, meaning in a standard GaN structure. So we are able to get 0.1 ohm millimeter, which is, even less than 0.1 with the regrowth. If I don't do regrowth, your question is correct, that it's very difficult to make ohmic contact with it. But regrowth solves that problem.
So we have a few more questions. People are very interested about your talk and they are enthusiastic in putting questions. So one more question is that what is the maximum channel temperature in case of aluminum nitride HAMT? I think aluminum nitride HAMT can sustain very high channel temperature.
Indeed, yeah, thank you for the question. And you're right, Janish, also about it. In fact, you mentioned Professor Kubal, the channel temperature that was measured in the ALN HEMTs that we have made. We shipped the samples to him, to their group in Bristol, and they measured it. And what they show is for the same, they did a comparative study for the same DC voltage on the drain voltage, etc. They see a 40% reduction in the channel temperature by using ALN buffer and the GaN channel structure compared to the GaN substrate layers. That work will come out soon, but the maximum channel temperature, I don't know, but for the same bias conditions, it is causing a 40% reduction in the channel temperature. That's what we have measured. Actually, not we, Martin has measured, Kubal has measured it.
Yeah. Okay, so next question from Mr. Rakesh Kaneria from SSC again. Recently, 2D materials integrated with gallium nitride heterostructure. Can this heterostructure have potential for single photon source detector for quantum communication?
Absolutely. I think 2D materials have both an advantage, but sometimes a headache of the fact that you can put it anywhere you want, with a Scotch tape, put it sort of anywhere you want. So, and 2D materials sure can, I think semiconductor-based single photon detectors can be made for example, one of the best ones would be an avalanche photodiode, right? An APD. APD can do very good single photon counting. But a single photon counting is very difficult with semiconductors if you are in the microwave domain. I think Decisive was asking earlier about the microwave part, right? So in the microwave, you need a very small gap to detect that single photon. And for that, semiconductors don't work because the gaps are much larger than the microwave photons. For optical photons, there, of course, 2D materials can be as good as a silicon APD or a gallium arsenide APD or a GaN APD for that matter. So I would still go with the APD. It is a well-behaved device. People have sort of used it and designed many nice circuits with it. But 2D materials, sure, why not? I mean, I think if you have to be able to also isolate it from the environment, because every little noise, single photon detection is a game of noise as well. So I think you have to isolate it properly. As long as you do that, why not?
Yeah, one last question we are taking from YouTube, and rest of the question I ask our participant to mail to you so that you can reply.
Okay.
Yeah, this question is, what dictates the choice of carrier substrate for Josephson junctions? This is by Mr. Santanu Sinha.
Yeah, thank you, Shantanu. This is actually a very good question, and definitely not something that has an answer that everybody agrees on. From all my conversations with people who are actually making microwave quantum qubit-based circuits, not single device but circuits, the substrate of choice right now is sapphire. For all the people who are making very large density circuits. But people are also investigating silicon carbide, and of course, the king of all substrates, silicon, is still in the game. But looks like sapphire has a little bit of advantage in terms of very low noise, very effective decoupling of all kinds of things that are desired in quantum. So right now, that is what several groups are looking at. But I would say that it's not something that everybody agrees on.
Okay. So thank you, Professor Jaina. Now our director wants to our today's speaker.
Thank you very much, Professor Deepta Jaina. It was a wonderful talk, and I think the promises that gallium nitride holds, whether it is in the RF or in the tera or in the quantum zone, and that you have brought out through your talk, is definitely very, very exciting. And it's been a very, very enlightening talk for all, I would say. And I'm really so happy by the extensive question answer session that you've so patiently handled and so well. So thank you very much. I think I was sitting there was just thinking that we could not have had a better choice for a JC Bose Memorial Lecture than you today. So it is wonderful. I would just now request our chief guest to give his concluding remarks before we end.
Thank you, Dr. Seema. And at the outset, let me now once again thank Dr. Devdeep Jaina for his very exciting and illuminating talk. And this semiconductor physics and devices is one area which I had never understood. But today, at least, you have rekindled that urge to learn about that with your talk. And I really felt very interested. And I also hope that all our audience who are there from SSPL and other participants, especially from my center here at Space Application Center, and from the questions were asked, I really feel that it has generated a lot of curiosity and interest into this very exciting field. And as I said, uh, of course, SSPL is working on these devices and other technologies. And at SAC, at ISRO also, we are now embarking on developing this photonics and electronics related marriage, and especially learning about semiconductor and superconductor, how to, this quantum enemies, how to do the marriage, as your Cornell University paper says. So that is one area which it would have given a lot of insight to all our people. We had planned this session for only almost around 1 hour or 15 minutes, and we are inching towards almost 2 hours. So that itself shows the interest your talk has generated. And as I said, it is a really very exciting field. A lot of people in SSPL as well as ISRO are working and trying to work on these new technologies. And you have opened up a new world of these nitride semiconductors with various possibilities. So we really hope that it will, in India also, somebody will come out with a lot of activities related to not only physics part of that, but also the development and technology part of it. And it will really feed into the various development. Of course, we are application engineers in ISRO and other organizations here, but we eagerly look forward to these new devices. And of course, there are challenging areas related to efficiency, yield, and then temperature management and thermal management, about which people were asking. So that will need some work to do, but I'm sure that it is going to open up new technology domains for the whole world itself, not only for US and India. So once again, we thank you for a very exciting talk, and we hope to remain in touch with your team there and with you in particular. Because as I said, all of us are going to work on these new areas of research. and development. Especially, as I said, we want to develop from now. We are right now working on microwave technologies, but we are slowly moving on to millimeter wave and sub-millimeter wave. And then we have plans to, as I said, from quantum communication right now within the free space on Earth, and then in future on satellite-based quantum communication, followed by quantum radar. So all these are distant areas which already has been identified in this country, and this orientation will of course help us to learn more about this exciting field. So sir, thank you very much for, and we are keeping you awake at a very late time
Yeah.
of yours. So sorry for that, and thank you very much once again. Thanks.
Thank you, sir, for your kind words. Thank you, Professor Jena, for staying late. You are awake now. Yeah. Thank you so much. So with this, we conclude this session, and I want to acknowledge all participants. Thank you very much, Dr. Sharma, Dr. B.K. Segar, our DG Medcos, Dr. Varghese, Dr. Amita Gupta, all participated, and all audience here put many questions that were interest to all of us. And so with this, I want to thank you, our director, Dr. Seema Vinayak, for continuously motivating us to organize this lecture, and it was a successful event. So as a convener of organizing committee, I would like to thank Ms. Deepti Mongia, Mr. Deepak Sharma for their hard work to make this event successful. I want to acknowledge the help of Dr. Subhash Chandra for his support in organizing the event. Dr. Raghavin Saxena, Shri Abhishek Sharma, Shri Mohanlal in preparation of invitation cards, banners, and all the members of card invitation and distribution committee who spared their time to distribute the invitation cards. Dr. Sanjay Toma, Mr. Ashok Kumar for logistics, Mr. Pankaj Kumar, Mr. Ravi Kumar, Mr. Mahesh Kumar, and Mr. Neeraj for IT support. Mr. Chinkesh from DIT&CS, our DRDO headquarters, to make this event international on YouTube. Mr. Ashish Jindal and all members of Works and Canteen Committee for venue management. Thank you all. Thank you very much. Now I invite the attendees present here in SSPL for a cup of high tea outside our SJB auditor. Thank you, sir.
Thank you, Dr.
Thank you, Mr. Kaushik. Thank you, Mr. Nilesh and Dr. Seema, for the invitation. Very grateful, and hopefully we keep in touch. And if there are any further questions, please just send them. We're very happy to reply and answer.
We'll get back to you, sir. Thank you.
Good night, and thank you. Enjoy the tea.
It was